page 2, example 2. We start with this right here. We're going to give you a derivative. The derivative is equal to y. The other way to say that is that the derivative of this function will always be equal to the y value of the function. So we're going to draw a slope field, and I'm going to start it here, and then I'll pause and fill it in for you. So we'll start first with, we'll start up at the top, and we'll say, well, what happens when y is equal to 3? Well, if y is equal to 3, then that means that for all of the values where y is equal to 3, which is this horizontal strip right here, the slope is going to be 3, so it's going to be fairly steep. So it's going to look like this. So if we are at a height of 3, then whatever this function is, it's going to have a slope of 3. Alright, so I'm going to take a moment, draw in the slope field. If you want, you can challenge yourself, pause the video, and see if you can draw in the slope field, and then come back and start the video again and see whether or not you have the same slope field that I. Alright, so here's my slope field over here. Perhaps yours looks sort of like that. And then with that slope field, what we can do is we can get a solution for this. What happens if we know that the function goes through the point x equals 0, y equals 1, and again we have a function that goes through this point, x is equal to 0, y is equal to 1, and it has at all places its slope is equal to its y value. Right? So we start at 0, 1, which is right here, and then we're going to flow up following the slope field. So we're going to get a function that's going to look sort of like this. Here we are, the slope is 2. As we get higher up, now my slope is 3, and I'm moving up. And then in here, my slope is going to be 1. When I get down into here, my slope is going to be 1/2, and I'm going to just go this way. And this should be, the purple function here should look kind of familiar to you. Alright, so now again, algebraic solution to this. For C, we're going to solve this algebraically, and we're going to do something which we're going to refer to as separating out the variables. We're going to start with the differential up here. And the differential again is dy over dx, and that's going to is equal to y. And I'm just going to throw this 1 in here, 1 times y, and you'll see y, no pun intended, you'll see y in just a second. What I want to do is I want to get the dy on one side, I want to get the dx on the other side. In fact, I want to get all of the y's on one side, all of the things pertaining to y on the left side, all of the things pertaining to x on the right side. So I can rewrite this as 1 over y times dy. That's on my left side, and then on my right side I'm going to end up with 1 times dx. So equivalent equations, and in the same way you can multiply an equation, left side of an equation and the right side of an equation, and keep it equivalent. We're going to take the left side and the right side of this equation, and we're going to find the integral of each side. I'm going to find the integral of the left side, and then I'm going to find the integral of the right side. And the integral of 1 over y dy is the natural log of the absolute value of y. One of those integrals that you need to have memorized. Plus c. Put the plus c here for a moment. It's going to go away in just a second, and I'll explain that. And then over on the right side, this is just simply going to be x plus a c for this side. And we can call this over here a c1, and we could call that a c2. And then the c's, this c here, I can bring it over to the other side of the equation by simply subtracting c1 from both sides. And then, whoops, that's not c1, sorry, go back. c1, I'm subtracting c1 from both sides. And then over here on the right hand side of the equation, this c2 minus c1 is also a constant. And I can give that a new name. I could call that c3 if I wanted to. Instead, the way that we're going to do this is we're not going to put the c on the right side, and we're not going to bother with subscripts on these c's, because these constants, we don't know what they are. We can just simply combine them into one constant, and I'm going to combine it into one constant over here on the right side. So again, the integral of my differential equation becomes a natural log of the absolute value of y, which is equal to x plus c. And now, if I take and use this as an exponent and use this as an exponent on the same base, e to the natural log of y on the left, e to the x plus c on the right, then this simplifies to the absolute value of y on the left and e to the x plus c on the right. Here we'll just do this. E to the x plus c. This is absolute value, which means that this whole expression over here could either be positive or minus. So we're going to write this as positive or minus. And then I'm going to take the e to the x plus c, and I'm going to rewrite that with the constant part first, which is the e to the c, times the variable part, which is e to the x. And then what we have again is we have this constant over here. This piece right here is just a constant. So some number, we don't know what that number is, it depends on what this value c is, but some constant times e to the x. Which, if we look at our graph up here, makes sense. This graph is an exponential graph, and we pinned it to the point 0, 1. But if we're doing this in general, we don't know exactly where it gets pinned, and that pinning, where it ends up vertically on our graph, is determined by this constant right over here that's in purple. Right? And then in general, what we've just done by taking this differential dy dx equals 1y and separating the variables and integrating, we've determined that the differential dy dx equal y comes from a parent function that is of the form some constant, and we'll call that constant a, times e to the x. Okay, I'm going to try and speed this up now. I'm already at 18.5 minutes. I was going to try to keep this notes to under 20 minutes, so we're going to try this. The next couple examples I'm just going to do step by step, pausing in between, which hopefully will make it go quick for you. You should try these on your own. I think there's been enough explanation that you can do these on your own, but you should then use this video to check to see whether or not you're getting them correctly. Okay, so here we go. Speeded version. 1, I rewrite the equation, putting all of the stuff pertaining to y on the left, all of the stuff pertaining to x on the right. Write the square, put everything in fractional exponent form, integrate both sides. Again, we're going to use just one constant, and the constant's going to hang out over on the right side of the equation. Notice I've divided everything by 2, and in doing so, over here this constant is actually half as big as this constant, but since we don't know what the constant is, we're just simply going to continue calling it c. And here we go, we have the general form of the parent function, which has a derivative of square root of y divided by x squared. Okay, now example 4, we're going to look at the differential equation here. This is our derivative that we're looking at. So again, verbally you can think of this as a function whose derivative is always equal to the opposite of the x value of the point divided by the y value of the point of that function. Right? So we're going to draw a slope field for you. We'll do that now. Okay, so if the x value is 0, then the slopes, no matter what the y value is, the slopes will always be 0. So that's these little red slopes that we have right there. And then if the y value is 0, then it doesn't matter what the x value is, because the slopes are all going to be undefined. So that means that the slopes, whenever y is equal to 0 here along the x-axis, those slopes are all going to be undefined. Those are all going to be vertical. Alright, and now what I've done here in green is I've marked all of the places where the x value and the y value are the same, which means that the slope would be 1 or negative 1. Right? So each one of these little green segments shows me where the slope is going to be either 1 or negative 1. And then the blue segments here represent the places where the y value is twice as big as the x value. And if the y value is twice as big as the x value, then the slopes are going to be negative 1/2 or positive 1/2. And each one of these blue slopes is either a negative 1/2 or a positive 1/2. And if you take a step back, maybe look at this kind of squinted, what you're starting to see is that these slopes look like they're describing a circle. And now if we take this and we look at, go here to problem C, we're going to now take the differential dy dx equals negative x over y. This is describing the pattern in the slopes. And again, we're going to do this technique of separating the variables, get all the y's onto one side, all of the stuff that's x on the other side, integrate both sides, and then solve. And when we do this, I'll go through this step by step for you. When we do this, we will indeed get the equation for a circle. All of the y stuff on the left, all of the x stuff on the... We're going to integrate both sides. And again, when we integrate, you're going to end up with a constant over on the left side. You'll end up with a constant over on the right side. We're just simply putting both of those constants over onto the right side and just calling them c. I've multiplied both sides by 2, and again, this c down here is twice as big as this c here because I multiplied the equation through by 2, but since I don't know what it is, I'm just going to continue calling it c. And lo and behold, what we saw in the slope field, the pattern of the slopes here in the slope field, is indeed what we get when we take the differential equation and we bring all the y's to one side, all the x to the other side, we integrate, and then we solve. And there we go. This right there, y squared plus x squared equals c, is indeed the equation for a circle.